In this video, we're going to solve a problem involving two-dimensional displacement. Here's the scenario. The pilot first flies 12 kilometers due north, and then he flies 14 kilometers in the direction 22 degrees east of north. And then he flies 11 kilometers due east. And our goal is to determine the helicopter's total displacement. To get started, let's visualize this with a diagram. We'll set up a coordinate system where the positive y-axis pointing north and the negative y-axis points south, and the positive x-axis pointing east, the negative x-axis points west. Now we have the coordinate system. Let's draw the journey of the helicopter. The first part of the journey is 12 kilometers due north. So we can represent this with an arrow pointing straight up along the y-axis. And the length is 12 kilometers. And next, the pilot flies 14 kilometers in a direction 22 degrees east of north. To draw this, we'll start from the end of our first arrow. From here, we measure 22 degrees eastward from the north line. Okay, we rotate the north line 22 degrees eastward. So basically it's from the north line, rotate 22 degrees eastward. Okay, there's going to be 22 degrees. And the length of this line will be 14 kilometers. Now the third part of the journey, the pilot flies 11 kilometers due east. So we need to start from the tip of the second arrow, and we draw a new arrow, and this one 11 kilometers long, pointing straight to the east. 11 kilometers. So these three arrows, we call them displacement vectors. We can label them as delta D1, delta D2, and delta D3. And the little arrow on top of this D is a reminder that each of these is not just a number, it's a vector that has both a specific length and a direction. Okay? To find the helicopter's total displacement, we need to add all these vectors together. To add these vectors, we just draw one final arrow that goes from our very first starting point, okay, which is here, this is the starting point, to the tip of the last vector, which is here. Okay, and this new vector is the total displacement. Okay, it tells us the helicopter's final position relative to the starting location. This is how you add up the vectors graphically. When you add up the vectors, you draw the vectors one by one from the tip of the previous one. Okay, doesn't matter how many vectors you have. So the sum vector is always starting from the starting point to the tip of the last vector. So you draw an arrow. So this is the sum of these vectors. Okay, now that we have the diagram, our goal is to calculate the length and the direction of this final displacement vector. We'll do this by adding our three vectors, delta D1, delta D2, and delta D3, algebraically. It's important to remember that you can't just add their lengths together like a simple sum. Okay, adding 12 kilometers, okay, 14 kilometers, and 11 kilometers would give you a distance traveled. Okay, so this will give you the distance, but not the final displacement. This is not the displacement, because these vectors are pointing in different directions. You can only add the vectors by their magnitude, okay, or by their lengths if they are pointing in exactly the same direction. For example, if you walk 200 meters east and another 100 meters in the same direction, Your total displacement is a simple sum, which is 300 meters east. But if you were walk 100 meters in a different direction, let's say you walk this direction, your total displacement would be something like this, and it's actually less than 300 meters. It's not 300 meters. Okay, so you can only add them up by their lengths if they are pointing in the same direction. If the vectors are not in the same direction, to add them up, our strategy is we'll break down each of these vectors into its horizontal and vertical components. Once we have those components, we can easily add all the horizontal components together and all the vertical components together. Okay, we can handle them separately. Let's start by breaking down the first vector, d1. This one is simple because it's a pure vertical displacement. Since the pilot flew directly north, there's no horizontal movement at all. We can write this as delta d1 in the x direction is 0, and delta d1 in the y direction is 12 kilometers. Okay. Next, let's look at the delta 2 vector. We can do this by drawing a line from the end of the vector parallel to the horizontal axis. Okay, and a line from the start of the vector parallel to the vertical axis. We can think of it this way. The delta d2 displacement is the same as a path that goes vertically north, okay, this much, and then horizontally east. So these are the two component vectors of delta d2. The horizontal part of this path is the x component of delta d2x, and the vertical part is the y component, which is delta d2y. Since we've created this right angle triangle, this angle here is 22 degrees. We can use the basic trigonometry to find x and y components. Okay, let's find the y component first. We know that the cosine of an angle is equal to the adjacent side divided by the hypotenuse. In our triangle, that's cosine 22 degrees equals to the adjacent side is delta d2y and divided by the hypotenuse, which is delta d2. By rearranging this equation, we can solve delta d2y equals to delta d2 times cosine 22 degrees. We know the magnitude of delta d2 is 14 kilometers, and cosine 22 degrees is 0.93. Then we have delta d2y is approximately 13 kilometers. Now for the x component, the sine of an angle is the opposite side divided by the hypotenuse, and that gives us sine 22 degrees equals to the opposite side, which is delta d2x, divided by the hypotenuse, which is delta d2. Now let's rearrange this. Delta d2x is delta d2 times sine 22 degrees. Again, delta d2 is 14 kilometers, and sine 22 degrees is 0.37. Then we know delta d2x is approximately 5.24 kilometers. We've now broken down the second vector into its y component and x component. Now we'll move on to the third vector, delta d3. This one is also straightforward because it's a pure horizontal displacement. The helicopter flew straight east, which means there's no vertical movement. So we can write its components as delta d3x is 11 kilometers, and delta d3y is 0 kilometers. We have now successfully broken down all three of our displacement vectors into their horizontal and vertical components. Now that we have all these components, we can add them up. Since all the x components are pointing along the same axis, we can simply add their values together. The total x component, delta dx, is the sum of all the individual x components. So it equals to delta d1x plus delta d2x plus delta d3x. And let's plug in the numbers. We have delta d1x is 0 plus delta d2x is 5.24 kilometers plus delta d3x is 11 kilometers. So it equals to 16.24 kilometers. We'll do the same for y components to find the total y displacement. So delta dy equals to delta d1y plus delta d2y plus delta d3y. Plugging in our values, delta d1y is 12 kilometers plus delta d2y is 13 kilometers and delta d3y is 0. So we have 25 kilometers. So now these two values, delta dx and delta dy, are actually the two components of the final displacement, delta d. Essentially, we've transformed this problem into a simpler one. The pilot's journey is equivalent to flying 16.24 kilometers east. He flies in this direction, 16.24 kilometers, which is delta dx, and then 25 kilometers due north. And then this is delta dy, which is 25 kilometers. Now we have this red-angled triangle. This is red angle. We can use the Pythagorean theorem to find the magnitude or the length of this final displacement. And the formula is delta d squared equals to delta dx squared plus delta dy squared. So this is Pythagorean theorem. To solve for delta d, we take the square root of both sides. So delta d equals to the square root of delta dx squared plus delta dy squared. Let's plug in the numbers. Delta dx is 16.24 kilometers squared plus delta dy is 25 kilometers squared, then root. So eventually we get delta d equals to 29.81 kilometers. So the magnitude of the total displacement is approximately 29.81 kilometers. So this is the length or magnitude of the final vector. And now be careful, we haven't finished yet. The displacement is a vector, and so far we've only determined its value or the magnitude. We still need to find its direction. To find the direction, we'll use a little more basic geometry. let's define the angle, which we'll call theta, measured from the east line towards the north line. Okay, so let's find this angle, theta. You can also try to find this angle, which is measured from the north line to the east. So that's also fine. Here, we're going to calculate this theta. In this right angle triangle, we know that the tangent of an angle is equal to the length of the opposite side divided by the length of the adjacent side. Tangent theta is opposite side is delta dy divided by delta dx. Okay, so let's just write it down here. Tangent theta equals to delta dy divided by delta dx. And delta dy is 25 kilometers. Delta dx is 16.24 kilometers, which approximately equals to 1.54. And then theta is the inverse tangent of 1.54. Then we have theta equals to 57 degrees. So our final displacement has a magnitude of 29.81 kilometers and a direction of 57 degrees from the east line towards the north. So we write it down as east 57 degrees towards north. Okay, so this is the direction. To quickly recap the process for solving this type of problem, we follow these 5 key steps. In the first step, we draw the diagram. We begin by stretching a diagram to visualize each of the individual displacement vectors as well as the final displacement vector. And then we break down these vectors. So break down vectors. We broke down each individual vectors into the horizontal and vertical components. Okay, and then we sum the components. We add all the horizontal components together and also add all the vertical components together. Okay, then we find the magnitude. Using the Pythagorean theorem, we combine all the total components to calculate the magnitude or the length of the final displacement vector. And in the last step, we determine the direction. We use the basic trigonometry to find the angle and determine the precise direction of the final displacement. Okay. This is the process. So by following these steps, we were able to find the helicopter's total displacement from its starting point. Okay, I hope this video was helpful in explaining how to solve a two-dimensional displacement problem. If you found this tutorial helpful, please give it a thumb up and consider subscribing for more physics tutorials.